Hey everyone, let's talk about a word we all think we know, work. But what if I told you that in physics, its meaning is, well, it's probably not what you think at all. Let's get into it.
Okay, let's kick things off with a little scenario. Picture this. You're at the gym, you grab a 50-pound dumbbell, and you just hold it. Perfectly still. For a whole hour. I mean, your arms are shaking, you're sweating bullets, it feels like the hardest thing you've ever done. So here's the question. According to a physicist, are you actually doing any work on that dumbbell?
And the answer is a big, fat no. Yep, you heard me. In the world of physics, you've done absolutely zero work on that weight. Zero. It sounds totally nuts, right? I mean, your muscles are screaming at you. But to get why, we've got to toss out what we think work means and learn the real rules.
Okay, so if that's not work, then what on earth is? Let's totally rebuild our idea of work from scratch. And it all starts by understanding the difference between how we talk and how physicists talk. And this right here, this is really the core of the whole thing. See, in day-to-day life, work just means effort. It's labor, it's toil, it's just trying hard. But physics? Physics couldn't care less about how tired you feel or how much you're sweating. It's looking for something very, very specific.
The thing is, the scientific definition of work is actually super simple. It comes down to just two really strict rules. And if you don't check both of these boxes, no work has been done. End of story.
So here they are. Rule number 1. You've got to apply a force. A push or a pull. Simple enough. But here's the kicker. Rule number 2. That force has to actually cause the object to move. It has to cause a displacement. If nothing moves, no work is done. And that right there is why holding that weight still is zero work. You're applying a force, for sure, but the displacement, it's zero.
All right, let's get a little more formal. The textbook definition says work is the product of two things: how far something moves, and, this is the really important part, only the piece of the force that's actually pointing in the direction of that movement. Yeah, that's right, not all of your effort might count.
And this brings us to the little bit of math that unlocks this whole concept. The formula is work equals force times displacement times something called the cosine of theta. Work equals Fs cosine theta. And trust me, that cosine of theta bit, that's where all the cool stuff happens. So let's break this down. See this diagram? We're pulling on a block with a force F, but we're pulling kinda up and to the right. The thing is, the block is only sliding to the right. That's our displacement, S. That angle between our pull and the actual movement, that's theta. So what the cosine of theta does is it basically figures out how much of that angled pull is actually helping to move the block forward. The part of the force that's pulling up isn't doing a single bit of work in the forward direction. And this cool little formula reveals something even more interesting. It turns out, depending on that angle between your force and the direction of movement, work can be positive, it can be negative, or it can be zero. Let's dig into what each of those means. So, positive work is what you probably think of first. It's when your force is helping the motion. Imagine a horse pulling a cart. The horse is pulling forward, the cart is moving forward. The force and the displacement are basically lined up. That's positive work. You're adding energy to the system, making the cart move. Okay, but what about negative work? This is when a force opposes the motion. It's fighting against it. The perfect example is hitting the brakes in your car. The car is moving forward, right? But the braking force is pushing backward. That force is doing negative work. And what it's really doing is sucking energy out of the car's motion to slow it down. And that brings us back to zero work. Now, we already know one way to get zero work, if nothing moves. But there's a second really important way. If your force is perfectly perpendicular at a 90-degree angle to the motion, the work is also zero. Why? Because the math, cosine of 90 degrees, is just zero. Think about it. That force isn't helping the motion forward, and it isn't fighting it backward. It's doing nothing to it. This is a great way to see how multiple things can happen at once. Check this out. You lift a box off the floor. Your lifting force is pointing up, and the box is moving up, so you are doing positive work. But wait, at the very same time, gravity is pulling the box down. Since the box is moving up, gravity is doing negative work. Two different forces, two different kinds of work on the same object at the same time. All right, let's test this with another brain teaser. Think about a satellite in a perfect circular orbit around the Earth. Gravity is constantly pulling it in, right? Towards the center of the planet. So
as that satellite whips around the Earth, is gravity doing any work on it? What do you think?
The answer is nope, zero work. It's kind of weird, but it makes perfect sense. At any single moment, the satellite is moving tangent to its orbit, sort of straight ahead, but gravity is pulling it straight in, towards the Earth's center. The angle between its motion and the force of gravity is always a perfect 90 degrees, so gravity isn't doing any work to speed it up or slow it down. It's just constantly yanking it sideways to keep it in that circle. All right, you've got the rules now: positive, negative, and zero work. Let's put it all to the test with a quick pop quiz. So here's the scenario. You've got 4 identical boxes, and they're all sliding to the right. Now, each box is being pulled by a rope with the exact same amount of force. The only thing that's different is the angle of the pull, as you can see in cases A, B, C, and D. So here's your job. Rank these 4 from the one doing the most positive work all the way down to the one doing the most negative work. Remember the secret. W equals Fs cos theta. It's all about that angle.
Okay, got your answer? The correct order is D, then C, then B, then A. Let's walk through it. D is the winner for most positive work because the force is perfectly aligned with the motion. The angle is 0, and the cosine of 0 is 1, the biggest it can be. C is next. It's still helping, so it's positive work, but not as much as D. B is our zero work case. The force is at 90 degrees to the motion. And finally A, where the force is actually pulling backward, fighting the motion. That's our negative work. Okay, so we know how to define work. We can even calculate it. But who cares? What's the big deal? Why is this concept so important to physicists? Well, the answer leads us to another huge idea in physics: energy. Specifically, something called kinetic energy. And all that is the energy an object has just from being in motion. A bowling ball moving fast has a ton of kinetic energy. A ping pong ball moving slow, not so much. And here it is, the big takeaway. Work is the transfer of energy. That's it. When you do work on an object, you are literally changing its energy. Do positive work and you give it more kinetic energy, it speeds up. Do negative work and you take away its kinetic energy, it slows down. This link between work and energy is one of the most powerful, fundamental ideas in all of science. So we've seen that work is all about forces, transferring energy, and changing motion. So let me leave you with this little puzzle to chew on. If you push on a spring to compress it, you're doing work, right? And then when you let it go, the spring itself does work. But where did that energy go when you compressed it? And where did it come from when you let it go? Sounds like a great topic for another time.